Okay, so you saw last class the failure theories for ductile and brittle materials. Let's see if we have. I think we solved this problem. Okay, so we should have solved this problem. We'll continue with the next problem. Again, the next problem is similar. So I'm going to skip this because the methodology is same. I'm going to skip this problem and go to the next part of the chapter. So let's continue with fracture mechanics. Fracture mechanics is separate different topic on the failure theory of materials, especially under static loads. Okay, specifically we are going to go through linear elastic fracture mechanics. Before I continue, I have to connect my iPad. Okay. Okay, so what is linear elastic fracture mechanics? In linear elastic fracture mechanics, we are going to include the presence of cracks, macro cracks in a material. So, okay, so any material you take, it will consist of micro cracks and macro cracks. So first let's note down. Lecture 15, lecture 16. Going to be lecture 16, section 1. Okay. So until now, what we have seen, failure theories. Oh, this is not working. Great. I think I will have some problems now because the setup is not working here. Just hold on a second until I figure out why this is not working. Huh? No. I usually charge it and keep it ready. I think this is having problem because of getting connected. It has to get connected here. Let's see here. Not sure where it is connected. Just hold on a second, please. This cannot be the device. Network status, here Wi-Fi. Just hold on a second. The link is already provided in the chat here. Okay, so please connect through the chat.
I sent it to WhatsApp.
You sent it to WhatsApp, yeah. Okay. Since this is the first class right on the campus, I will have some hardware issues, so please bear with me now. So available networks, not able to see anything. Pen, no results. Touchpad, typing pen, and yeah, Windows Sync. What is the problem over here? Pen has a shortcut. No, it doesn't connect. Bluetooth and other devices. Yeah, this is the one. Apple iPad, USB. I'm not seeing my pen here being connected. What the hell is wrong? Okay. I think it should be connected here.
Yeah, it must connect in one Wi-Fi.
Actually here, yeah, this is the only drop pencil. Somehow this is Apple Pencil is not connecting. Don't know why. No, this is not writing. Keyboard. It's just waste of time here. No. No idea what is the issue now. Okay, so we will continue. I will have to see this. I will try to continue the class without the pen here. Let's see here if I can insert any text.
Very good.
Okay. Okay, so last class we went through some of the failure theories. What are the failure theories? Again, we will try to recall what are some of the failure theories we went through. And I have to increase the size. Okay. We went through ductile materials, failure theory. What are the failure theories? Maximum shear stress theory, and then we went through distortion energy theory. And for materials with two different values in the tensile load under compressive load, if you have two different values, in that case we went through Coulomb-Morse theory. Okay. Now, besides this, we also had failure theories for brittle materials. What are the failure theories? Again, we had only one failure theory, Coulomb-Morse theory. Okay. Now, as a third one, we are going to go through linear elastic fracture mechanics. In all the previous theories, we did not have any microstructure involved. Okay, so what is a microstructure? For example, information regarding your grains, any microcracks, etc. We did not include explicitly any parameters associated with microstructure or any other internal structure. In linear elastic fracture mechanics, we include macro cracks, information regarding macro cracks. Okay, so what is a macro crack? Any crack which is in the order of millimeters, few millimeters, or maybe slightly less than millimeter range, then it is called as a macro crack. Any crack in the order of micrometers, they are called as micro cracks. All your manufactured materials will consist of macro cracks and micro cracks. Okay, so in this case, we are not going to include the effect of micro cracks. It will require an advanced course to understand the influence of micro cracks. What we are going to include is presence of macro cracks inside the material. Okay, so let's go to the slide. Since I cannot write here, I will try to write it as much as possible, and we will go through the theory here. So the linear elastic fracture mechanics assumes cracks are present, macro cracks, and these could be due to flaws present inside the material. For example, if you have a material which is cast and cooled down due to the presence of inclusions, other types of manufacturing flaws and defects, cracks could develop inside the material as it cools down. When you have two different materials with a different thermal coefficient of expansions, and because of that, you will have cracks forming because you have different material properties within the material. So one material will try to contract at a different rate while cooling, while the other material will contract at a different rate, and because of that, internal cracks develop. Now, the presence of the internal cracks, what it does is weaken the actual strength of the material. So the material, if its actual strength is some 200 megapascal, as in the case of steel materials, because of the crack, the actual strength of the material can reduce quite significantly and may even reduce below 100 megapascals. Why does it reduce? Because of presence of cracks, there is a change in geometry. So you can think of the crack inside the material as a sharp corner like this. In this sharp corner inside the material, you will have very high stress concentration effects. And because of the stress concentration effects, the material will fail very rapidly. And specifically, we are going to use fracture mechanics in the case of brittle materials, because brittle materials are very sensitive to stress concentration factors. Okay. So what are some of the examples of the brittle materials? Again, we have glass, hardened steels, especially if you have cementite phase. The more the cementite phase is in the steel, you will have very hard materials, and because of the hardness of the material, you will have very fast crack propagation inside the material due to stress concentration effects. Again, aluminum, some aluminum alloys are also brittle, classified as brittle. We also need to take care of ductile to brittle transition temperature for each material, especially what kind of materials undergo ductile to brittle transition temperature. If you recall, it is BCC. BCC structured materials always have this weakness. FCC materials or HCP materials do not have ductile to brittle transition temperature. And if you take steel, steel has BCC structure. Okay. Okay. So brittle fracture might seem instantaneous from our point of view. However, there is energy that has to be provided or transferred to the cracks, and once the energy is transferred, then the crack propagation takes place. So there needs to be enough energy supplied to the cracks for the crack propagation to take place. So based upon this theory, Griffith, a guy by the name Griffith, he came with some models to predict when and how the fracture will propagate. So we are going to see that. Okay. So we can start with a simple example. Instead of a presence of a crack, we can assume that you have an elliptical hole in a plate. And in this elliptical hole, we are going to consider ellipse with a major diameter A and minor diameter B. So what will be a crack? We can take this ellipse to the limit where we have A constant, and we can reduce the minor diameter value B to a very small value. If you reduce it to a very small value, then the elliptical hole will behave like a crack. So that is the idea. We will take to the limit and then try to predict. So now you can see here, this is a formula for presence of an elliptical hole in a plate subject to merely tensile loads in the direction of y, and you have the sigma yy max value given by the formula 533 here. Here sigma is the nominal stress in the absence of any elliptical hole present in the plate. Okay, whatever will be the stress, nominal stress, that stress value we will consider here and multiply by this quantity, which acts like a stress concentration factor. So if you let B to a very small value, the stress concentration factor here will increase to very high values, and you can see here the maximum value of stress also increases due to stress concentration effects. So this is a very crude way of solving a crack problem, but there is enough theory and experimental research behind the crack propagation theory, and we will see better theories for the same. Okay. So when does crack growth happen? Crack growth occurs when energy release rate from the applied load is greater than the rate of energy for crack growth. So imagine there is a particular value of energy that is required for crack propagation to take place, just to start to take place. At the same time, we will need the energy to be supplied at a particular rate so that the crack propagation can continue. So if you apply an external load, again, we are talking about static loads here, okay, not dynamic loads, static loads. If you apply the load, enough load such that the energy that is supplied from the external load, okay, the rate at which the energy is supplied from the external load is greater than the energy required for crack propagation, then the crack propagation will take place. Unstable unstable crack growth occurs when the rate of energy release rate relative to crack length exceeds the change of crack growth rate of energy. So it's basically saying that if we have higher amount of energy than the energy required for propagation of cracks, then it will lead to unstable crack growth. Okay, so why do we call it unstable? Because crack propagation continues to take place with respect to time, so it is unstable. Okay. Now there are three modes in which crack propagation can take place. All crack propagation usually take place in mode 1. So what is mode 1 crack propagation? If you have a crack opening as shown in the plate over here, and we apply a load in the direction normal to the direction of the crack surfaces, and it leads to opening up of the cracks like this, then it is mode 1. Most of the crack propagation, even when you apply shear load or torsional load, whatever is the load inside the material, most of the crack propagation will take place in mode 1. Very rarely in mode 2 and mode 3. So in mode 1, the crack opens up in this direction. In mode 2, the crack is sheared in opposite directions. So this is very rare. This kind of crack opening is very rare. A third mode is off the plane shear mode. Okay, where you are tearing like a piece of paper. So mode 2 and mode 3 of crack opening, these are very rare, and if it takes place, we need a much more complicated mathematical formulas to calculate the energy required for crack propagation. Okay, again here some formulas are provided. Now we cannot go into the derivation of these formulas because again you will need an advanced course on linear elasticity to derive all these equations. Take it for granted. All these formulas you have to take it for granted. Again, here mode 1 crack, for mode 1 crack opening, you have list of formulas which are derived based upon linear elasticity. We have the sigma xx component, sigma yy component, and tau xy component. What are these? These are the stresses around the crack tip here. Okay, around the crack tip, the stresses developed, they are given by these formulas. Now theta is this angle, r is the radial distance from the crack tip. Why do we need these stresses? These stresses tell us when the crack is likely to propagate. Okay, so if it is a brittle material, these stress values tell us if it reaches certain critical value, then the crack will propagate. So we need some idea about the crack propagation. Now again, these stresses are derived on certain assumptions, plane stress and plane strain condition. Most of the crack problems analytically are solved as a 2D problem rather than a full 3D problem. We cannot solve as a 3D problem analytically. It is much more complicated to do that. We will need finite element analysis to solve the problem in full 3D, into a full 3D problem. So what do? We reduce it to a 2D problem. In 2D problem, there are two conditions, plane stress and plane strain. So what is the difference? Plane stress has only stress components which are in xy coordinates, in the xy direction. Therefore, sigma zz, you can see it as 0. Tau xz components, tau yz components, they are all 0. Okay. In the plane strain condition, it is the strain quantities which are 0, but not the stress quantities. Okay, so therefore you have the sigma zz component, but the other shear components are also assumed to be 0, especially under these types of load where we have only normal stresses. Okay, so let's continue. Now finally, we cannot use this formula given here directly. So we have 1 over r here. You can see as we reduce the distance r from the tip of the crack, the stress values increase to very large values. Now we are going to further reduce this formula from experimental observations with the help of a quantity which is called as stress intensity factor. So instead of calling as the stress concentration factor, what we are going to use is the stress intensity factor. Okay, and this is the factor we will be used in the calculations for crack propagation. Okay, so how do we define stress intensity factor? Stress intensity factor is defined in terms of nominal stress and the crack length. What is A? A is the crack length. You can see here, if you say this is the shape of the crack, assume this is the shape of the crack and half the length of the crack is A, assuming, and from the length of the crack substituted in meters, here in this formula we get what is called as the stress intensity factor. So you can imagine this stress intensity factor just like the stress, quantity stress. Okay, although we use stress intensity factor to calculate stress, you can imagine this quantity to be equivalent to stress for our calculations. Now, Ki again represents state of the material. Okay, it is not a material property, it represents state of the material. So let me write it explicitly here in the text. Represents state of the material just like stress, the quantity stress. Okay. Now, when we had failure theories with the quantity stress, we compare the quantity stress to a material property. For example, could be yield stress, could be ultimate tensile strength of the brittle materials in the case of brittle materials, etc. So in the same way, we calculate the state of the material by calculating what is called as the stress intensity factor in the case of cracks and comparing the stress intensity factor to a material property which is called as KIC. Okay, so what is this KIC? Let's go here. Before we go there, let me go a few slides forward and let me see if there is the definition called fracture toughness. Okay, so here we have a material property which is defined as critical stress intensity factor, KIC. So the I here again denotes mode 1 fracture. So this particular quantity material property can be used only with mode 1 fracture. Okay. Okay. Now, so KIC is the critical stress intensity factor, and we compare all the stresses we calculate with the all the Ki values we calculate, stress intensity factor with KIC values. So if your Ki is less than KIC value, then crack propagation will not take place. If it is greater, then definitely crack propagation will take place. So I should not write equal to here. It should be less than that. Okay, so this is the material property. Now let's go back for a second and discuss more about the calculation of stress intensity factor. Okay, so what is Ki? Ki obviously depends upon the geometry of your crack, size of the crack, shape of the crack, and type of loading or the mode in which the crack propagates. So specifically mode 1 crack opening. Okay. Now you may have different geometry for your component. You may have a cylindrical component. You may have a component that is shaped like a plate, maybe just like an axial bar, etc. So depending upon the geometry, the Ki value when calculated through, let's say, simulations, will give you different Ki values. Now, we cannot do that analytically, and therefore we include another factor which is called as the factor beta here, which is stress intensity modification factor beta. And this beta will be usually provided with graphs. And these graphs are very similar to your Peterson's graphs. And from these graphs, you will extract the value of beta and then calculate what is the actual stress intensity factor beta for the crack. Now, not only it depends upon the geometry of the component, it will depend upon the size of the component. It will also depend upon the type of loading. You may have a torsional load, you may have a bending moment load, or a combined load. Depends upon type of loading. Your beta values will be different. Okay, so we have to calculate Ki value depending upon that. So let's see those graphs. For example, if you have a plate and you are applying simply a tensile load in the case of the plate, and let us assume the crack is present somewhere inside the plate and not on the edges, then you will use this particular graph to extract the values of beta here. And the beta value will depend upon the ratios A over D and D over B. What are A? A is the crack length, half the crack length. D is the location of the center of the crack here according to the graph, and B will be the twice the width of your plate. So depending upon these dimensions, you can extract the beta value and then calculate the stress intensity factor. There are other cases. If you have edge crack in the plate, then you will use this particular graph. If you, in the previous two cases, you just had tensile load, normal to the crack direction. Here you have bending moment applied to the plate or a bar. And here you have a transverse load applied to the bar. So depending upon what is the condition, you can extract the beta value. Now let's see here. Another case where we have a hole present in the plate, under the edge of the hole, due to very high stress concentration effects, maybe crack developed, and you have particular crack here. Okay, so again, we use different graphs for that. If you have a cylindrical specimen, in the case of a cylindrical specimen where the cracks, here let's read through that. We have having radial cracks of depth A. So you have cracks, I think here radial cracks of a particular depth, and then in that case you will use this particular graph. Here the direction of the cracks you can see here, it is in the axial direction at a particular radius here. On the other hand, the direction of the crack here is radially located. So again, you will use a different crack depending upon the direction of the orientation of the cracks. Okay, so all these cracks are macro cracks which can be detected using your non-destructive testing methods. Okay, so we also briefly discussed about the stress intensity factor. Okay, so what is critical stress intensity factor? It is a material property, okay, dependent upon the material, the crack mode, processing of material, temperature, loading rate, and state of stress. So these are a lot of things. So how do we determine? We cannot determine these quantities just based upon theoretical calculations. We would rather require experimental procedures also to determine what are the KIC values. Okay. Okay. So again, this is for mode 1 fracture. You cannot use for mode 2 fracture, or a combination of modes of are present in crack propagation. Then we will not be able to use this. Okay. So how do I get KIC values? Just like you get the material properties like yield strength, ultimate tensile strength through an experiment, in the same way there are experiments available through which we can obtain these KIC values. Now you saw the formula for Ki and Ki. What is the unit of Ki? Go back to the formula. Since I cannot write, I will go a few slides back. And you can see here we have the quantity sigma. Sigma is usually expressed in megapascal units, and the A value is expressed in meters. So the Ki has a unit megapascal root meter, and that is the same unit we have for stress intensity factor, critical stress intensity factor, or fracture toughness, KIC. Okay, so megapascal root meter. So typically for aluminum, 2024 aluminum, very commonly used material, again you have different values. For titanium you have higher values, and in the case of steel you can see intermediate values. Okay, so what does this KIC value actually measure? It measures the amount of energy the material can absorb under static loads without undergoing fracture of the material or crack propagation in the material. So it tells you how much energy it can absorb without any crack propagation. The higher the value, the more the energy it can absorb without crack propagation. How do you calculate factor of safety? In the case of fracture mechanics, if you can calculate what is the stress intensity factor, and we know some parameters regarding the crack, then we can calculate Ki rather, and then we will be able to evaluate what is the stress intensity factor depending upon, factor of safety, depending upon the KIC value. Okay, so very similar formula. The material property on the numerator divided by the state of the material. Okay, that always gives you what is the factor of safety. Okay. Brittle fracture should be usually considered at low temperature operation, and where ductile to brittle transition temperature may be reached. Over there, ductile materials also need to be regarded as brittle materials. In the case of brittle materials, as usual, we need to do these calculations if we know there is a crack present in the material. So we'll go through a very simple example here. The calculations is extremely simple in this case. Okay, so let's see an example. We have a steel ship deck plate which is 30 mm thick and 12 meters wide. So we can draw a plate approximately, and this is 12 meters wide. I'm trying to draw with the mouse here, so bear with me. Okay, so this is the plate we have, 30 mm thick. So let me write 30 millimeters. It is loaded with a nominal tensile stress. We are directly given what is the stress, sigma. Sigma value is 50 megapascals. It's a tensile stress. It is operating below its ductile to brittle transition temperature. That means the material is brittle, and KIC value is given as 28.3 megapascal root meter. So there should be a unit root meter here. If a 65 mm long centrally transverse crack is present, so in other words, right in the center of the plate we have a crack. Okay, so let's assume this is the crack. through the thickness, 65 mm long. Estimate the tensile stress at which catastrophic failure will occur. Compare this stress with the yield strength of 240 megapascal for this steel. Okay. So how do we proceed? As usual, the first step is going to be calculation of your stress intensity factor or the state of the material. What is the state of the material? We are given sigma root pi A is the formula. We also have to multiply with the factor beta over here. Okay. So for the centrally present crack, we have to go back to one of the graphs provided here in the plate here. So this is the graph we will use, and we have to use the ratio A over D. You can see 2A is 65, and let's write it down here. 2A is equal to 65. Okay, and the D value is going to be right in the center here, since the width is 12 meters. We can take this as 6 meters and 65 mm. Okay. B is also equal to 6 because 2B is 12. B is also equal to 6. So we can calculate the ratio D over B. D over B is 1. So we will consider the curve here, the outer curve which is given here. Let's see the other ratio, A over D. A over D will be 65 over 2 times 10 power minus 3, which is a very small value. Okay, so A over D is going to be extremely small value, nearly 0. So we can assume beta equal to 1 in this case. Sorry, beta is equal to 1. So in our problem, we can safely assume beta is equal to 1. So we can neglect this term and calculate K. Now, before we do that, if you see the question, estimate the tensile stress at which catastrophic failure will occur. So if you want to calculate the stress at which catastrophic failure will occur, Ki should be equal to KIC value. So sigma critical root pi A times we have 65 over 2000 in meters. Okay, and that should be equal to your KIC value 28.3 megapascal root meter. And we can calculate what is the sigma C value from here directly. Because it according to the diagram, let's go back to the diagram here. We can see in the diagram we are given 2A. The total length is 65, so 65 divided by 2. Okay, so let's go back. Just hold on for a minute so that we can open MATLAB and calculate the critical value of stress. Check this. Okay. Okay, so we have pi into 65 over 2000, 28.3 megapascal. So we will leave it in megapascals, and in the denominator we have square root pi times 65 over 2000. Okay, be careful about the units. Always calculate in meters the crack length. So 88.57. Okay, so that is the critical stress value, 88.57 megapascals. So this is a very easy problem, not very tough. This is the stress at which the crack propagation will take place. However, the applied tensile stress is only 50 megapascals. So we are definite that there will be no crack propagation taking place. In fact, we can calculate a factor of safety based upon these stress values as sigma c over c. C over sigma value, actual sigma value. The factor of safety is actually defined as KIC over KI value. However, we know what is the KIC formula. KIC, we will obtain the KIC value by taking the sigma c value and multiplying by root pi a, and we will get the KI value by taking the sigma value 50 and multiplying by root pi a. So root pi a on numerator and denominator will get cancelled, and we can easily calculate our factor of safety as sigma c over c. So this also will give us the factor of safety in this particular case. Now you are asked compare the stress with the yield strength of the material. Obviously you can see here why do we want to compare. 240 megapascal is the strength of this steel. Normally, if no crack was present in the steel plate, then we can go up to 240 megapascals and no failure will take place. However, since the crack is present in the plate, we can clearly see it leads to failure much below the yield strength of the material. It's about at least 1/3 of the stress. So the presence of crack reduces the strength of the material greatly. Okay, so you have to realize this. Okay, so even in the static case, this is what we are seeing. So problem has been solved here. You can go through that. A different procedure is given. The way I solved it is different from the solution given here. Okay, doesn't matter. You can follow this method or the method provided by me. Okay. Next class on Tuesday, we will proceed with more examples of fracture mechanics, and we will be done with this chapter, and then we can move for fatigue cracks and fatigue failure theory. Okay. So see you guys, and I will meet you again on Tuesday. Yeah.